So the question is there any function that have countably infinite number of periods and the set of periods is dense in R? So the question is can we find any function that satisfy this property? So let us see. First we take a function, okay, a from R to R and the function defined by uh, f of x that equal to, this is a very well known function, 1 when x inside q and 0 when x inside q complement. This function is very well known function, the namely Dirichlet function. Okay, this function have the property that this function have countably infinite number of periods and the set of periods is dense in R. So how we have to prove this? Okay, we claim that this function has the property, has the above property. So now we have to prove this. So see here. Now what is our aim? So we know what is the definition of period, that is f of x plus p that equal to f of x. Okay, and it satisfy for all x inside R. Now in this question we have to find p, we have to find p. We have to check, basically we have to check that p inside q or q complement. Okay, so this is basically the definition of period, f of x plus p that equal to f of x for all x inside R. Now our aim is to find p, or you can say that we have to check p inside rational or not. Okay, so let us check this. Now what should be our approach? Okay, just a second. What should be our approach? Okay, so firstly we assume that p belongs to R. We assume this, then we can say that imply p belongs to q or p belongs to q complement. Okay, now we firstly we assume that p belongs to q complement. So assume this p belongs to q complement. We have to proceed and see what is its set inside q. Okay, now that imply x plus q that belongs to q complement. There is nothing to confusion. So now if we take this f of x plus p, what do you get? We get f of, that is what, that is basically a irrational number, right? X plus p inside q complement. So this is basically a irrational number, so we get f of irrational number, and the function defining that when x inside irrational number then function attain 0. So that basically 0. Is it equal to f of x? No. Why? This is not equal to f of x. Let me write this elaborately. What we get? We get f of x plus p that equal to 0 that not equal to f of x. Why? Because we take x inside q rational, and when x belongs to rational, f attains 1. So we know that 0 is not equal to 1. So f of x plus p is not equal to f of x when for all x inside where q. Okay, so this is fixed. See, we take p inside r, it implies that p inside q or p inside q complement. So first case we assume that p inside q complement, and the next case we assume that p inside q. Okay, so now the x also in r, so x inside q and x inside q complement. So we have already done the first case. We assume that x inside q, and we have already completed this. Now we assume that x inside q complement, that imply x plus p belongs to q complement when x not equal to minus p, and x plus p that inside q when x equal to minus p. Why? Because if x equal to minus p, then it is 0, and 0 belongs to, and 0 is a member of q. So these things happen. Okay, so let uh, let x equal to minus p, then what, x plus p inside q, then x plus p inside q, that is rational. So f of x plus p that equal to what? uh, Remember the function we define, when x inside q, then the function attains 1. So by the definition of our function, this value is equal to 1, but 1 is not equal to 0, that equal to f of x. Why f of x equal to 0? Because see here, we assume that x inside q complement. The first case we assume that x inside q, and the next case we assume that x inside q complement. And when x inside q complement, the function f of x attains 0, and we know that 1 is not equal to 0. So that imply f of x plus p that is not equal to f of x when for all x inside q complement. So what will happen? So we see that when x inside q or x inside q complement, the relation f of x plus p equal to f of x doesn't hold. But the definition of period, we know that f of x plus p that equal to f of x for all x inside R. Satisfy this relation for all x inside R. But what we see here the relation not hold for all x, because if we take x inside q or x inside q complement, we see the relation doesn't hold. So if we take just a second, if we take p inside q complement, then the definition of period doesn't hold. So what is our conclusion? Our conclusion is that p belongs to q is not a period, not a period of f of x, not a period of f. What is f? Previously we defined f. What is f? That is basically a Dirichlet function. Okay, so that is irrational number can't be a period of f, right? So now what is our conclusion? Our conclusion is that now, sorry, not conclusion, now we have to check if we take p inside q, if we take p inside q, then we have to check it forms a period or not. Okay, so the next case we assume that p inside q. Previously we see that the irrational numbers is not a period of f. Now we have to check is the rational number a period of f. See here, previously we claim that yes, we have a function that satisfies the following property. What is the property? That this function have countably infinite number of periods, and we know that the set of rational number is countably infinite, and it is also dense in R. So here is the possibility that this function may period in all the rational number. So let us check this. Okay, so next case we assume that p inside q. So similar case, so x inside, we know that in the definition of period, so f of x plus, what is the definition? F of x plus p, that equal to f of x for all x inside R. So see here carefully, for all x inside R, so we can break this x inside q or x inside q complement. So we break this and take two cases here. Okay, so for first case we assume that x inside q, both p and q, that inside, sorry, p and x inside q, then that imply x plus p, that obviously inside q. So f of x plus p, that equal to this inside q, so this basically inside q, then this is 1, this is equal to f of x. Why? Because we take x inside q, and when x belongs to q, then the function attains 1. We know the definition of function. So these things happens for all x inside q. Okay, the next case we assume that x inside q complement. So if x inside q complement, then the here the p is fixed. We assume p inside q, and and here is two subcases, one x inside q and x inside q complement, similar the above case. Okay, then x plus p, this inside q complement, this belongs to q complement, and so f of x plus p, that is nothing but irrational number. So this is equal to 0, this is equal to f of x. Why? Because x inside q complement, and when x inside q complement, the function attains 0. So these things happens. So x plus p, that equal to f of x for all x inside q complement. Okay, so observe carefully that when we take x inside q complement, q, and when we take x inside q complement, in both cases the definition of period is hold. So what we can say? We can say that f of x plus p equal to f of x for all x inside R, where p inside q. Okay, so when p inside q, then f has period, but when p inside q complement, then f has no period. So what is our conclusion? Now our conclusion is that conclusion now our conclusion is that the set of all periods of f is rational number, that is q, and we know that the set q is countably infinite and also q is dense in R. So that satisfy our given statement. So this completes our proof.